So yesterday we sort of discussed about all the range-based techniques, right? Most of the geometrical approaches, right, that we had to follow for constructing the topology of the system, right? Starting from the anchor locations, and from there we used primarily three techniques. One was the angle of arrival, time of arrival, and time difference of arrival. So two based on ranges. The time of arrival technique was directly the range, whereas time difference of arrival was the difference of ranges. So in case of time of arrival, we looked at the range equation, and you also knew the location of the anchor. From there we could construct a circle, and if you have multiple such anchors, you could take the intersection point of those circles and figure out the location of the point. And what was the other way? We were, instead of looking directly at the time of arrival data, we were trying to use the TDOA, or time difference of arrival, and that had some unique advantages over uh, calculating time of flight, because you do not have to use a two-way communication as we did for TWR or two-way ranging. So we can use this TDOA to scale up the process, right? It could be that the anchors are simply broadcasting, and all the devices receive simultaneously, and based on the time difference of the received messages from each one of these anchors, we could actually calculate the location of the device itself. Okay, and that was primarily an intersection of several hyperbolas, right? It was a difference of Euclidean distance, not just the Euclidean distance is equal to something which was representing a circle. In case of the range equations we looked at the first couple of classes, and the TDO is a little bit different, where we look at the difference of the Euclidean distances that gives rise to the equation of an hyperbola. Okay, and after that we also looked at angle of arrival, because the angle information combined with the range can give you also access to location, right? In that way, if you have angle combined with the range, you might not need three ranges, right? As I told you, that if you know r and theta, so you can locate yourself as like r cos theta and r sin theta, right? So x and y, you do not need R1, R2, and R3. That has to be calculated from three anchor locations. But in that way, also you can scale up the process. And sometimes it is also necessary, if you are just interested in the direction of arrival information, right? In those cases also, it could be useful. And we looked at how we could calculate the angle of arrival based on the difference of phases. So we learned this formulation about how the phase difference relates to the path difference of the different waves that we are receiving in this individual antenna, and how the resolution of that angle is related to the separation of distance in between the different antenna elements. Okay, so how large of a physical structure it will be, that depends on the wavelength, right? That relation we have kind of understood yesterday, right? So I would request you to revisit them, right? And they primarily form the fundamental techniques by which you can solve localization problems in a geometric sense. Okay, there is one more thing that I'll mention today, right? I'll not go into the like nitty gritty details of that, but I'll give you enough pointers as that you can explore that on your own. So earlier, whatever we have understood or looked at was both this information was available, right? So somebody also we were discussing, right, that sometimes this anchor information or the expectation of this availability of the anchor information might be impractical. I mean, who is going to tell you where exactly the XY coordinates where the anchors are located? So if you are trying to do a one-time deployment, right, in a big shopping mall or some airport kind of scenario, it might make sense. But let's say you want to do an ad hoc deployment, suddenly you want a localization service to be on. That calibration phase might take a long time. So you have to go and measure the location and then put that access point or that anchor there, right? So this is time consuming, and also it is not scalable. If you want to cover a large area where you need to place anchors, it's not going to be It cannot be done in a very quick way. Okay. So but that was it, right? Though that was those are the assumptions when we used TOA, TDOA as well as AOA. But currently what we are trying to look at is, are there any way such that we can reduce the dependence on the information regarding the anchors. Okay. So that is what this information may be present or absent. Okay. So maybe it is partially present. Maybe for some anchors you know the location, and for some anchors you do not know the location. Okay. And that's why we just say, right, this information collection of such information requires extensive human efforts for deployment and calibration tasks. So sometimes we can do a deployment, right? The deployment could be random, but the calibration is an extensive it requires extensive human efforts. Okay. So this is mostly manual labor that you might have to use. And sometimes in situations like disaster management, or let's say the military wants to go somewhere and they need this kind of an ad hoc localization right now and right there at that time, so they might throw some of these anchor devices randomly, right? There could be let's say a small like ball kind of a thing, right, that has, let's say, camera, and that has wireless transmitters embedded in it, right? They could simply throw that ball in that zone, right? And that ball could also transmit the video, right, how it moves around. And after some time, when it settles down, it also becomes an anchor. It starts communicating with the tags owned by the first responders or owned by this military personnel. Okay. So but only problem is that we do not know the exact location where the anchor is deployed, right? The ball just moves naturally, and then it stops somewhere, right? And this is more of a random deployment. So they can, the deployment is not that difficult, and sometimes it is like really necessary to have localization in situ, but we do not have the time and the energy to do calibration. Hope the motivation for that is very clear. Okay. And so this could be that we do not have such information. What do you do in such cases? Okay. So ranges we still have, right? Please try to understand the premises, right? We have ranges. Okay. And the we have the anchors. Do not think that we do not have anchors. There are nodes or there are beacons who are going to range with your device. Okay. What we do not have, we do not have the coordinates of the anchors. Okay. So it's basically, you can think that you have a collection of nodes, right, whose locations are unknown, and your device's location is also unknown, right? So in that sense, these things become more of a homogeneous system, right? So you have, earlier we were calling them anchors because we knew their location and we use them as a reference point. But currently, let's say this is your this the green node is your node, right? And the red nodes are sort of the whatever we used to call them as anchors, right? Currently all of them are the same, because for nobody I know the location. Okay. So I am trying to solve the location for this, but at the same time the locations of this whatever we used to call anchors, they are also unknown. Okay. But you can perform ranging, doesn't matter, right? You can always know the distance of this unknown of this anchor with my IoT device. Okay. So this is possible. Okay. So this information is not known, that is what I have written there. So in this current situation, there is practically no difference in between whatever we call an anchor and our device, right? So think about it. They are capable of ranging with a device that is the location of them are not known, right? So in practical scenario, right, in practice, all of them would be able to range each other. Okay. And what we are trying to get at is, can we try to build this topology? Okay, so can we try to build this relative geometry? What is topology? Topology is just the relative geometry. Okay, so because we do not have any location coordinate to start with, right? These are all floating in space, right? We do not know where are they at all. But what we can do is that, let's say if we assume this as like a 0 0, let us consider it's a 2D system. The localization is going to happen in a 2D plane. So let's say this is 0 0, then all other points are going to be at a fixed distance and a fixed bearing, right? A fixed angle compared to the this reference anchor, right? You can always call one anchor or one point as 0 0, right? There's no harm. That becomes your coordinate space, because unless or until you start with a coordinate space, the localization does not make any sense, right? Because location itself is deeply embedded in a coordination in a coordinate system. Unless and until you know the coordinate system, that xy doesn't make any sense, right? So in this case you can say that, okay, given that this is the origin of my coordinate system, what exactly will be the location of the different anchors? Okay, so we will start with the process of ranging, right? And think of this as a graph, right? This is basically a graph, right? Where you might have edges. If the edges are the links in between the two nodes, right? In between two, these are I am going to call them nodes, because currently there are no concept of any anchor and beacon separately, because all of them are just nodes. They are at unknown location and they can range with each other. Okay, so they are all nodes, and based on these nodes they could be vertices of the graph, right? So these nodes are the vertices of the graph, and these are the edges, the links where you are calculating or estimating the range. These are the edges. So based on these things, right, you can come up with an adjacency matrix, right, where I can put the weight as if the edge exists, I can put the range value as an entry to that matrix. Okay, so that is exactly happening here. So let's say if you have 8 nodes, right, and you know the distance in between all of them, right? So let's say this is a complete graph in this particular case. So you have 8, choose 2 number of edges, right? And this is the matrix which we call as the Euclidean distance matrix, or EDM. Okay, so we have to know the topology or the relative geometry of the nodes given this information. Okay, so let us say this is your topology of the graph, right? Where you have these nodes. Let's say one. Let me change the color here. So 2, 3, 4, 5, 6, 7, and 8. So you have 8 nodes, right? And so you have a 8 cross 8 matrix on the right hand side, and I have already given you the entries of them. It's a symmetric matrix, right? I need not mention, because the distance between A and B is same as the distance between B and A. Okay, so this part, the lower left part, is paired, right? But still you need 8 C2 different entries. Okay, now there is a technique which is known as multi-dimensional scaling, or MDS, right? That can give you this embedding given a correct EDM matrix that is complete. Okay, so this is often studied as a part of, let's say, dimensionality reduction, right? Sorry, I did not put the, yeah. So this is often studied as a part of dimensionality reduction or feature selection kind of techniques in machine learning, right? So you can look, like if you have taken a course on machine learning, I'm sure that you will come across techniques like PCA, uh, as well as this multidimensional scaling, which is going to look at this set of feature vectors and then try to embed them in a certain space, right? Let's say a 2D space. Okay, so similarly here also, yeah, sorry. Okay, So that is the sole job of this particular algorithm, right? Whereas the other way around is very trivial. If given this graph, you can very easily come up with this Euclidean distance matrix. This part is very easy. Okay, so you basically have in square algorithm, right, that can take the graph and compute the EDM. But my problem is different. Our problem is, given the EDM, can you come back to the topology? So this is our problem, in this case the problem of relative localization. Relative localization. Okay, so this is not trivial. Okay, given the EDM, how do you come up to this topology? This problem is not very trivial, because think about it, not all the EDMs could be just given a random matrix. You won't be able to do it, because it might not be, first of all, a valid EDM, right? For being a valid EDM, you have to satisfy all the triangular inequalities, for example, right? So these are the nodes that actually have certain coordinates, right? Let's say this is 0 0, so this is like 0 comma 3. Okay, so um, this is, let's say, sorry, this could be, this is the x-axis, right? So it will be 3 comma 0, right? So this is, let's say, 3 comma minus 7, and so on, right? So it has to satisfy the distances that you are providing, right? So this is basically going to be 3, right? So let's say this is x is equal to 0 and y is equal to, let's say, minus 8, right? So this is basically going to be 8. So these numbers that you are providing in the EDM has to satisfy a certain structure, right? If these are all some random numbers, you won't be able to come up with a unique geometry. That might not be possible at all. Okay, and also bear in mind that in a practical situation, you are going to also have errors in it, right? So you are not going to be given the exact value of the range, but this 3 is going to be having also some noise component. Okay, so there's 8, but there is a noise, so you might actually get something like 8.79. Okay, you might actually get something like 3.68. Okay, so this will be a noisy range. Okay, the range will not be perfect. So the MDS algorithm, and but there are other algorithms, right? MDS is basically the starting point, can take care of such noise. Okay, so this is also solved as an optimization problem, and I'm not going to go into the details of MDS. Normally it is anyway taught as a as an ML in an ML class, right? And you can look it up. I mean, I'm going to give you the reference pointer, and you have to basically sit down and try to understand how MDS works. Okay, so you need some background in linear algebra. Okay, so eigenvalues, eigenvectors, you need to understand. So is this clear? Why the inverse problem becomes difficult and the straightforward problem coming from the graph, right? If you come from the graph to the EDM, it is an easy problem. But going from the EDM to the relative localization is like you need to use certain techniques, right? It is not as trivial as computing the EDM from the graph. Okay, so is this particular thing clear, what we are trying to do? Or let us consider this MDS as a black box. But given whatever, considering MDS as a black box, suppose you are given the code, did you understand the premises? Who is an anchor, or what are the nodes, who is ranging with whom? Are there any confusion? Okay, so the only problem here though could be with rotation or translation kind of a thing, right? I thought some of you would ask this thing, right? So although the topology is fixed, right, but this topology can also be satisfied if this entire picture is reflected in a mirror. Okay, so if you think imaginary, if you think of an imaginary mirror here, okay, and you simply reflect this figure, okay, on the other hand side, it is just going to be a mirror image, right? It is just going to be flipped. Okay, and still it is going to satisfy the EDM. The EDM will be still satisfied. Okay, so in that way, the topology that you are going to get would be a reflected version. Number two is that this entire structure could have a rotation. Okay, so this entire structure could be rotated. Okay, if this one is 0 0, let's say if this 8 is considered as 0 0, it could be rotated with this axis. Okay, this could be, think of a like vertical pole, right, like a vertical stick kind of a thing where 8 is attached, and this entire structure could swing. Okay, still your EDM is going to be satisfied. Okay, and also translation is possible. If you take this eighth node and shift it to some place, right, let's say instead of 0 0 you make it 5 comma 5, so the entire structure is going to shifted by 5 comma 5, right, 5 in the x direction, 5 in the y direction. Okay, so that is where we cannot give you guarantee about absolute location of the nodes. Okay, so if you can fix these things, only then you can have an absolute localization. Okay, so you have to make sure that at least the location of one node you know in the physical geometrical space that we are talking about, not in the hypothetical geometrical space here, right? Here anybody can be 0 0. Okay, but you have to assign that particular node a certain value in the coordinate space you are interested in. Okay, otherwise it will only be a relative localization. If you want to uh, want to have an absolute localization, in that case you actually have to assign a physical coordinate or associate a physical coordinate with a certain node here. Then you at least save the problem of translation. Okay, so it cannot move around arbitrarily. Okay, and then if you can fix the angle of one of the nodes, right, at least you know the direction of arrival or something like that. In that way, suppose you can fix this particular angle, right, at least one of this or at least one of the nodes, right, then this entire structure becomes rigid. It does not move, right, it doesn't rotate also. Okay, reflection you need to solve similarly, right, maybe with respect to some other device that has some other node, right, based on whether two nodes are nearby or far, or whether it's on the this side of the building or that side of the building. In that way you can figure out. Okay, so primarily the first part was relative localization, and the second part is that how do you associate some physical coordinate with a certain node to translate this relative localization to absolute localization. Okay, so this is basically the technique, and the technique that we use is this multidimensional scaling that takes these features, right. In this case our features are basically the distances, and this layout these distances on a 2D plane, and that basically becomes the topology. Now the problem that you might have are missing ranges. Nobody is guaranteeing that you are going to have all the ranges, right, because if there are certain ranges that could be missing. Okay, so in such cases what you are going to do, because MDS will require a matrix that is complete, right, so if your ranges are missing, you have to first fill them, right, without that you cannot construct the graph, right. And suppose you try to construct the graph, right, let's say you on pen and paper you try out to lay out the topology, right, without using any algorithm. You just have 1 2 3 4 up to 8, and just look at their distances and try to lay them over, right, 1 2 3 4 5 6, you draw them on a piece of paper, 7 and 8, you look at the distances. Okay, what is the distance between 1 and 2? 12. What is the distance between 1 and 4? 56. Okay, what is the distance between 1 and 6? So in that case you have to connect 1 and 6. Yeah, in this case it is not connected, but still let's say you actually try to assign these values and try to figure out the topology, right. The problem is that with some of the ranges that are critically missing, there could be ambiguities in this particular topology. Okay, what is an ambiguity? The ambiguity could be, let's say this 2, node number 2 could also be here. Okay, so that it does not change the relative localization of the nodes that it is connected to. 2 is connected to 1 and 3 here, by these two arms, right? This 12 and let's say this is, I don't know, maybe 17. Even if it goes there, it still remains 12 and 17, but the location has become changed. This is like 2 prime. Okay, so that is also a possible incarnation of the graph. Okay, which basically makes this entire structure what we call as non-rigid. Okay, so think of this as flexible. There are certain nodes that can have ambiguous positions, right? So maybe there are other nodes that were related to 2, right? Because it was depending on 2. If 2 was here, they would create a certain geometry. If 2 was here, there could be other nodes like 16, 17 and so on, that had a certain distance relation with 2, that will also start changing. So at the end of the day, if you have any flexible components within your graph, the entire graph is going to be flexible, and the relative topology that you are going to get is erroneous or ambiguous. Okay, so I would not say so. There could be multiple possibilities, and one such possibility would be the correct EDM. Or it would be the correct topology. The EDM, whatever is data is supplied to you, it is all correct. Okay, but that EDM, whatever is given to you, is insufficient to guarantee a rigid topology. That is all I am saying. It's not guaranteeing a unique topology. It is guaranteeing some topology that could be ambiguous, right? For example, I have given you this instance, right? 2 could be on the left hand, like on the south side, or 2 could be on the north side. Okay, which one you are going to choose? And now given that where you choose 2, there could be other nodes that are directly connected with 2. Okay, for example, here I told about 16 and 17. Now 16 and 17 would have been here, 17 and 16 could have been here. If you take the decision of 2 being on the south side, if it goes to the north side, it will be in some other place. There could be other nodes that are connected with 16 and 17, so the location of them also changes, right? So it could be either here and here or here and here. Okay, so you need to ensure rigidity. Okay, so this is another very important problem where you need to understand what are the missing ranges, like, or what are the ranges that you need at the minimum to ensure rigidity of this particular space. Let's say whenever I insert certain important ranges here, the system becomes rigid. Right now, 2, I give one more association of 2 with some other node. Now 2 has become, 2 cannot move. This is fixed, right? Let's say this is R1 is fixed, R2 is fixed, and this is R3. These 3 are fixed. With respect to 3 nodes, let us say that those are fixed. Okay, this is a triangulation kind of a scenario. Think about it, because we are already assuming the locations of these things are not changing. Well, if it is changing, it is a different story. But if it is not changing, the L1, L2, and L3, we do not know L1, L2, and L3. We do not know the values of L1, L2, and L3. But what I am saying, that I am at a fixed distance from these 3 nodes, which by definition defines my location. Okay, my location cannot be ambiguous. Okay, so in that way you can do it for all the nodes, and that is what MDS optimizes this thing for, right? And you will get a unique topology. Yeah, but for that you need to ensure, and then there are certain checks for which you can ensure rigidity of a graph. So there is something which is known as a Laman graph, right? Let me mention, and if you are interested, you can look it up. There is a Laman graph, right, which can give you minimally rigid graph, right? Minimal number of edges that you will require in that particular graph to make it rigid. Okay, you can study more about it if you are interested in graph theory, or if you have background in graph theory. This is more of a graph theoretic problem. Okay, so the other problem is that given some of these values that will ensure rigidity, can the other ones be predicted? Yes, because if I'm ensuring rigidity of the structure by assigning some of the edges that were critical, the rigidity, if it is assigned, if it is already known, for example, on the left hand side figure, now let's say the figure is rigid. If it is rigid, you can know, okay, what is the distance, what is this distance, let's say. This can be derived analytically. You don't have to really go and measure. Okay, or what is this distance in between L2 and L3. Okay, or what is this distance? Even if you do not have a direct measurement, you can still derive them, because the system has already been proved to be rigid by the selection of the edges that we have done. Okay, so this can be predicted, and that is the problem, or that is the good part, is that we do not need all of them. Okay, we need a minimal, there could be a minimal subset that will be needed to ensure rigidity, and you do not need the rest. Okay, and that is what you need to range with. So if you have, in the beginning we started with, let's say if you have 8 nodes, right, you have 8 choose 2 number of ranges that were required, right, which is basically going to be a big number, right, n into n minus 1 by 2, right, in this case, because that is the number of entries on the top, right, so 8 into 7 divided by 2. Okay, whereas you do not might not need so many entries. Okay, so because if your n is going to increase, right, if your n becomes, let's say, 10, so in that case you will have 10 into 9 divided by 2, that is 45. So you need like 45 ranges. And remember, this entire ranging operation took so long, right? It could, if it is a two-way ranging process, if you do TWR, it might take like tens of milliseconds, right? So if you take, let's say, with all the process being done and some of the computation, everything, right? Let's say you can do something like 50, you can take 50 millisecond per range. So if you take 50 milliseconds per range, and if you have to do, let's say, for 10 nodes, if you had to do 45 range measurements, right? So that will be 45 multiplied by 50 millisecond, right? Which is greater than even 2 seconds. Okay, so it will take 2 seconds just to complete one location update for the entire topology, because, and your MDS is also going to take some time. Once you gather just gathering the ranges takes 2 seconds or more than that, and maybe let's say 500 milliseconds for running this MDS and throwing out the result, right? So it is somewhat going to take you close to 3 seconds in order to get a single location update. Frankly, this is not scalable, right? Because what if the nodes start moving? Because 3 seconds, you cannot guarantee these nodes to be just sitting quiet, right? They can start moving. Okay, so now this is a design question, right? And I have like thought I'll ask you here, right? What are the things then you have to ensure in this particular problem to make sure that the localization system works smooth? And what is the what is the criteria of being smooth? First is the locations that we are deriving for these nodes need to be accurate. Okay, I would say relative localization, because let us not bring in the absolute localization in this particular context. So relative localization needs to be accurate, and the responsiveness, okay, or the latency has to be minimal. Okay, so what exactly is the design problem that we are trying to solve here, or what is the research question? Right, some of you already have some research background, right? So given this context, I have already shown you the kind of problem that has to be solved, and we are assuming, let's say, a mobile topology, assuming a mobile topology of nodes. Okay, we are assuming a mobile topology of nodes. We need to be first accurate, and we need to have a decent responsiveness of the location update rate. Okay, you have to give me a location. So this is like something like an SLA. You have to give me a location every 1 second, or you have to give me a location every 2 seconds. There could be a certain criteria. Okay, so what you are going to optimize for? What is your design goal here? By design I mean algorithm design. Design goal, what you are going to, how you are going to think, right? Any pointers? So if you understood, like, you don't have to understand this entire thing mathematically, right now, but given the kind of background that I have given you, what should be your design goal in order to design such a system?
Sir, you should try to find the minimum number of ranges which are required to give a rigid graph.
Okay, true. Anything else? Yes. So that is what I have mentioned, right? Why are you saying minimum? It has to be connected, right? If you try to connect those dots, you will get it. So what you are going to do at every time instant? Just think in that way. I mean, you are in the correct direction, right? We have to, of course, minimize. If you don't minimize the number of edges, what is going to happen? What bad thing is going to happen?
Sir, you will have more range measurements, so you will lose time.
Okay, very good. So at every time instant, what you have to do? So time is flowing, right? So time is continuous, time is flowing, and everything is mobile here. Think about it. Then let's say you are tracking a structure that has, let's say, 5 nodes. Okay, so these 5 nodes could be 5 firefighters who have entered a building and they want the relative location of them all the time. Okay, so this is the graph, right? This could be the ideal thing, right? But you might not be able to realize all the edges. Okay, but another bad part here is that they are not fixed, right? They are continuously moving at a certain velocity. So one thing that you have to keep in mind, that the velocity has something to do, right? The velocity, if the velocity is too high, so based on that, you should adjust your range measurements, right? That is number one. And my question was that what you are going to, what is the main design problem, right? What I am not asking you how to solve it. I'm asking you what you are going to do at every time instant. There is a decision that you
It is
need to take.
like a measurement of the velocity of individual nodes, sir. That is a
Measurement of
challenge.
the velocity, how you are going to do.
No, so that is a challenge one, sir. Like here.
I mean, that is more of a challenge, right? If you
Yes.
if you if you had this velocity, that would have been a good thing to have, right? But let's say you do not have idea of the velocity, because if you get the relative localization done every time instant, indirectly you will get their velocity. Okay, so in that way you can get their velocity. But what you are going to do, my question is that every time instant, what is the decision that you need to make? I'm not asking how you are going to make the decision, what decision you are making.
So whether the topology also changes, sir, like
Topology
due
is
to the movement.
continuously changing, right? Yes, they are mobile, so they are just like, think about like 5 cows. You have put them in the field and they are running around. You have to tell me that what is the topology of those 5 cows at every set. That is an SLA, right? I tell you every 1 second or every 2 seconds, you have to tell me. But
Sir,
how are you going to spend those 5 seconds or 2 seconds? What are you going to do?
sir, maybe every second you only make a fraction of nodes range with each other.
Okay, and let us not yeah, true, but let us, I'll try to give you, so everybody, you are giving the correct answer, but we have to think in terms of time slots and not really seconds, right? We are, this entire thing will never be able to come up with a correct topology, because you need instantaneously all the ranges together in order to compute the correct topology. That is not possible, because I cannot have simultaneous range measurements because of interference reasons, or it has to strictly follow a TDMA schedule, right? Because we are assuming that we are trying to get a range measurement, which is going to be a time of arrival measurement. So consider every slot. Okay, so this is basically how you want to design this problem, right? So these are slots, and at every slot you have to decide which pair to measure. Okay, because your range is basically in between some nodes I and j, right? And you have this EDM sitting in front of you. Okay, let us not consider this part. So you have this EDM sitting in front of you. So all these entries have to be continuously be updated. This EDM always has to be fresh. Okay, If it becomes stale, because some of the entries might become stale, it's like too old. Okay, so in that case, you have to really update them. And what is the reason you might not have to update a stale entry? Can you tell me?
So if that node has not moved?
It's not that if that node has not moved, the relative location of the nodes has not
Yes.
changed.
Yes.
Okay, j could be moving, but I is not moving. That does not mean that ij is not changing. Okay, so if the relative distance between them is somewhat static or not changing rapidly, the duty cycle at which you need to update individual entries are going to change. So now your thinking should not be just related to the entire EDM, because I know that the EDM is out of control. You cannot get an entire snapshot of the EDM that is correct at any instant in time. What you can do, you can try to do a best effort. What is the best effort? I want to make sure that I will try, given the number of ranges that you can perform per unit time, you can only do, let's say, k measurements. So let's say within 1 second, 1 second has passed, this is 0 seconds, you have only have the luxury to take k measurements. Okay, and just doing this k measurements, how do I ensure that I have done the best possible job for ensuring rigidity? Yeah, that's all. I mean, as long as we can ensure rigidity, of course this will be correct, right? So if the rigidity is ensured, the localization will be somewhat accurate. Okay, so note that with even as time flows, things change quite a lot. Okay, so whenever you are trying to do this measurement in between nodes m and n, okay, rij has already changed. Okay, so you need to make sure that how much rij has. If ri by whenever you are trying to do get the range measurement mn, if rij has really changed by a huge margin, then the EDM that you are going to construct here at this point is going to be invalid. Okay, but it's not going to create a rigid topology. So that is the challenge here. Okay, and if you are interested to explore this further, you can take a look at this paper, right? That was like, now this thing has become much more mature, right? This is a paper that was published in the early 2000s, right? And this is pretty much known thing, right? How can you do this MDS for multidimensional scaling for node localization in sensor network? So you have this collection of these nodes, and they have made some idealistic assumption also that like if you can range with each other, what kind of how can you use this MDS algorithm in order to get the relative location. Okay, so one more question: why do you think we have missing ranges? One is that we are not able to calculate them in time, right? We are too slow, right? But other than that, is there any reason we should have missing ranges?
Sir, maybe the nodes are too far off, too many obstacles in the middle, so we can't
Yeah.
get a real estimate.
Yes, there could be non-line of sight, or there could be obstacles in between two nodes. They are outside the communication range of each other. Okay, so in that case, you cannot really have a complete graph. Okay, it could be that the communication in between them is cut off, and you might not. You have to only go to J via some other node. It could be through L, right, or it could be through M. Okay, in that way, you have to localize that with respect to I. Okay, so there could be missing ranges that is outside your control, because the topology of the network is such that they are outside the communication range of each other. So in that way, you cannot have that range even if you want to. I mean, it could be necessary that but that particular range is going to give you rigidity. Okay, but it is not possible to get that range. So there is a slight deviation from what some of these algorithms will directly, the naive algorithms or the Bayes algorithms, right, that have been developed in this context are trying to do. They will give you a minimal subset of edges that are required, but your problem is different. Some of the edges are might not be possible to measure. So in that way, you have to take those constraints into account and modify the algorithm accordingly. Okay, so these are like some of the research pointers, right? How do you want to design such a range measurements or range scheduling system in a mobile scenario, right? This is an interesting problem for somebody to look at. Okay,
So
So
always it is straight line distance only we are measuring, sir, in all the cases.
yeah, distance means straight line distance.
Okay, because any there is no non-linearities existing.
No, I mean distance is the straight line path, right? Be it LOS or NLOS is a different thing, right? So,
Okay.
but distance is means the straight line. This distance, that's all. I
Okay,
mean, otherwise it
because
doesn't make sense.
in always we measure like Euclidean distance. It is for only
Euclidean,
straight
yeah,
line.
Always we
Yes.
measure the Euclidean distance. Yes,
Okay, sir.
in whatever I have discussed.
Yes, sir.
Okay, okay. So now we have looked at some of these analytical approaches, right? And I would also say geometric approaches, right? Where we have some information or geometry about the topology, and we are trying to infer that. Okay, so we had ranging with infra. When I said infra, it means infrastructure. So infrastructure is needed on the left hand side. That box, the red box, I have assumed that infrastructure is needed. Somebody has to go and deploy those anchors and mark them. Hey, this is at 5,7, this is at 2,3, and so on. Somebody has to do that. So infrastructure is required, of course, which you don't like. It will be expensive. Okay, but nonetheless, that is like a fundamental technique from which everything came from, right? And we still, wherever it is manageable, we will try to use them, right? There are actually big startups which are selling such systems, okay, to give you indoor localization in wherever or in whatever context you need that, right? And we saw some slight variations like TDOA. How can things scale up using TDOA, which is very much like a GPS like system indoors, as you have seen. But that comes with this catch: you have to come up with a synchronization procedure in between the nodes. That could be difficult in wireless. The synchronization is a very difficult problem. Okay, things can go wrong. Okay, and we also looked at this AOA approach. Okay, so these are some way to determine the geometry of the system, and we also saw how to solve those equations using linearization, right? One was using the Taylor's theorem. I gave you one direction in that way. Then we looked at this matrix methods. Then we also looked at how do you solve using nonlinear least squares, for example, and we saw some library. That LMFit is a very useful library. I don't know how many of you had the time to go through it, but this is a very useful library that could be used for solving such problems. You can simply understand this in a better way, right? You can play with these things, and I asked you actually to implement that, right? So if you implement that, if you have any problems in implementation, you can come back to me. But I don't think it will be a very difficult problem. Okay, and then the other thing, everything holds. Okay, whatever we have discussed, everything holds. Just that we do not have any reference to those anchors. We do not know the anchor locations. Okay, so this is ranging is still there, but just that we don't have any anchors. And there were two problems. The first one was the matrix completion, because this matrix itself was incomplete to start with, because you have to first know what are the crucial ranges there, and the rest of the entries could be predicted, given that the already existing entries ensure the graph rigidity. Okay, so there is a matrix completion problem, and then there is this embedding. Okay, how do you take this one dimensional features, in this case these are just distances, right, and place them in the 2D space such that I can infer the geometry or the relative topology of them. Okay, this is very commonly used in understanding what do you call uh, like topics, right? In clustering topics, for example, right? If you get a feature vector and look at take those feature vectors in a 2D plane, some of those feature vectors will be all together, and some of the feature vectors will be all together, and there will be some distance in between some clusters. In that way, you can do things like topic modeling, right? You can know, okay, these feature vectors come from very similar topics. These feature vectors come from very similar topics. In that way, you can use also this thing for dimensionality reduction. Okay, so what are the features that actually dominate such that they create this clustering? So there is a lot of application in machine learning and NLP using multidimensional scaling. Okay, so lots of demo, lots of tutorial is available, and the Python libraries, right, this scikit-learn, or this is scikit-learn, I think they already give you a ready-made function that implements MDS. Okay, you have to just go and read it up and run this thing. Okay, but I request you to actually understand a bit of the theory, because if you just keep on running this thing, right, sometimes you will get results that are correct and sometimes you will get incorrect results, but then you will not be in a position to understand why it is incorrect or what is going wrong. You have to have some minimal understanding of how the MDS algorithm works. Now, coming from the analytical approaches, there are machine learning approaches also. Okay, so sometimes it is not possible because of the complexity of the hardware or the access to the hardware that is needed for computing range. Okay, so there are approaches which are known as fingerprinting approaches that I have discussed in the very first class, right? We spoke about signatures at a certain location. How does the signature of a particular signal look like? If we know that, that is also a good way to localize, right? And the other thing that is also infrastructure free is IMUs. Okay, IMU is your inertial measurement units, right? Inertial sensors that all of you have in your smartphones, right? So this is a combination of your accelerometer, gyroscope, compass, magnetometer, and so on, whatever you can derive from, like what is your heading, what is your acceleration in a given direction, okay, what is the angle that you are making while you are walking, that is basically your heading. Okay, so those information could be derived from the IMU, and sometimes we just use the IMU itself to localize. Okay, we don't need any other reference point. Your reference point is where you started from, like wherever you are starting to walk from, that is your 0 0, and from that position you keep on walking. Okay, you go 5 steps to the front, then you take a right turn and move 2 steps, and then you take a left turn, then you move 7 steps. Like that you are going to be tracked, and mostly it will be using some statistical filters like Kalman filters, particle filters. There are like extended Kalman filters. Those kind of statistical tools are used in order to track the location given this raw IMU data. So we are going to look at this IMU, some theory of IMU, and some of the other things, including tracking or simple gesture recognition tomorrow. And today I'm going to touch over the fingerprinting techniques. Okay, and ML models, like there are probably thousands of models now, because this is a very this was like or had been a very active area, still now somewhat active, where people are going to try out different sorts of machine learning models in order to get a better localization accuracy given the fingerprint data. Okay, so this is again somewhat dependent on infrastructure. So this is actually heavily dependent on infrastructure. Okay, here you only need the infrastructure for location of the anchors, right? Location of anchors. Okay, that is why you needed the infrastructure. This is what you have to calibrate. What is calibration? Calibration is like collecting your label data. What is label data? You need a label ID and then you need a feature vector. Your feature vector basically is your fingerprint or the signature, and your label ID is the location. Right? L1 you get this feature vector, L2 you get this feature vector. Okay, so each of these feature vectors are going to be different for different techniques people use. Commonly they will use some function of signal strength. Okay, or whatever is more fundamental is the channel state information. Okay, we looked at channel impulse response, right? We are going to also look at the frequency domain component of that, which is basically the channel state information. Okay, so let us look at concentrate on this, right? I would refer you to a couple of papers that were written in the very fast phase, right? Those are very simple, right? And those are not really practical. Okay, but you are free to explore this. There are like thousands of papers published in this particular area, right? And you try to concentrate. If you have a research background or you want to pursue research in this particular direction of localization, and that could be the reason you have taken up this particular seminar or this short-term course, right? So you could actually look at very standard papers where they are trying to use sophisticated ML models, or trying to use a combination of phase or channel state information in order to derive the location. Okay, so first, because we are going to concentrate on path loss or the received signal strength, right? RSS or DC, because I mentioned RSSI, right? This is a received signal strength indicator, okay? But this is directly, it could be mapped to the actual value of the received signal strength, okay? So we have to understand how the signal propagates in order to have some idea about RSS. Okay, so this is where an access point is shown on the left hand side. This is a Wi-Fi access point, and on the right hand side or in the middle, I show the smartphone that has the Wi-Fi interface. Yeah, and with distance, the RSS, I won't say RSSI. So RSSI is an indicator which basically could be mapped from, let's say, 0 to 100. Okay, it's going to be normalized from some value to some value, and it has a mapping from the signal strength. Okay, so this is RSS, I would say, like received signal strength. So RSS is not computed in the base station. The RSS is being computed here. What is the received signal strength, not the transmitted signal strength, and that is going to change with distance. Okay, so sorry, there is some issue with the, okay, okay, so received signal strength is basically, it is going to change as you increase the distance. Okay, so if you take the distance in the logarithmic scale, right, instead of the actual distance, we will see why. The This data is actually a data that has been collected in reality, right? We actually have done some experiments to collect this data. I am going to show you the demo, right? Some of the slides came up. You will see the demo soon, where the distance data was collected, and we take the log of that, and there is some concrete theory behind that. Why this can be a linear equation. Okay, what is the linear equation for the received signal strength versus the logarithm of the distance? Okay, and what is the reason behind that? The path loss at a distance d. What is path loss? The path loss is basically the difference of the transmitted power and the received power. How much of the power was lost in that path? So you started with energy 100, and when you reach home, you are left with energy 30. So how much of energy you have lost? 70. Right, so that is how, similarly in this case, you transmit at a certain power, right? You transmit at some 5 dB, 10 dB, and so on, and when you reach the receiver, your signal is at, let's say, minus 30 dBm, okay, or minus 40 dBm. So in that way, you can know that how much dB was lost. Okay, and so dB, whenever we talk about dB, that is in the logarithmic scale. And the actual power, if you see the path loss at a distance d, this is without logarithm. Okay, so path loss at a distance is just the power is in watts, is proportional to d by d naught to the power n, where d naught is basically a fixed distance, and we know what was the path loss as distance d0. Somebody has measured it. What is the path loss at distance d0? This is known. Okay, so if you know that, you can find out the path loss at any distance d by using this formula. Okay, the proportionality constant are going to come from this known value. And what is this n? This n is the path loss exponent. Okay, so this is exponentially going to deteriorate with distance. Okay, so this n, or often alpha, right? So this both alpha and n are used. This value can be like 2. It is very much similar to an inverse square path loss, right? Often this term you have looked at in, let's say, electrostatics or like Coulomb's law. Whenever you have studied gravitation, you already have seen that how the magnitude of the field decreases, right, as an inverse square of the distance. But in case of wireless path loss, it might not always be 2. It could be 2, 2.3, 3, depending on the medium, okay, or depending on the channel. Okay, if there are too many obstacles around, it could actually, the effective path loss could be more. Okay, and when you take a log of this particular thing and adjust the proportionality constants, you get an equation like this. Okay, and this is an equation which is linear. It is linear in terms of log d. Okay, because this will be log d minus log d0. Log d0 is known. PLD0 is known, because that is the calibration measurement that you have done. You have at least know for a fixed distance what is the for a given distance what was the path loss, that you know. From that you can derive this equation, and this PL at D, from this how do you want to get the received RSSI, or the received signal strength, the transmit power, right? This is the power of transmission minus the path loss. You know, this much you have already lost. So this is your received signal strength, or power of received at a distance d. Okay. So now this could be, so now you have a relation. Whenever we are basic in localization, we are just sniffing for factors that depends on distance. That is our only goal. Okay, can we find out a relation that exists with distance? We have gotten one. We can leverage. We can try to leverage this. Okay, so what will be the case? We have to just simply fit a straight line, because we have a concrete theory supporting that, and the theory tells us that it is supposed to be a straight line, and of course there will be some measurement errors, right? So these errors will be there, and that is going to give you some kind of a range error. Okay, we are just trying to use a different technique. We are not using channel impulse response. We are just using the RSS data, received signal strength data. So it is often known as the log linear path loss model, because you already understand why it is linear, or why it is log linear. When you take the logarithm, it becomes linear. Okay, so RSSI is equal to the slope multiplied by distance plus the intercept. Okay, so if you know the distance, right, what is the distance from the transmitter, you can know what is the RSSI based on this equation. Okay, and at the same time you can also know what is the distance given the RSSI, right? You can do the reverse computation, because this is a straight line. You know y is equal to mx plus c, so you also know x is equal to y minus c by m, right? That is what we are trying to do. So once you have this straight line that is calibrated for that particular environment, that signal strength data could be used to compute the distance. Because in localization I don't have the distance, I have the RSS. The signal strength is measured. Now, given the signal strength, can you tell me how far you are from the transmitter? What is your range? Okay, so that is how this thing works. And what is the error? Let's say you have this RSSI, which is basically, let's say, some minus 30 dBm, right? So it's not dB is just the path loss, but the received signal strength will be in dBm. Let's say minus 30, I don't know what is this, minus 32 maybe dBm. Okay, so this is your received signal strength. So if you look at your straight line that we have just now fitted, it is going to tell me that at this particular signal strength, this is the point on the straight line, and this is your estimated location or estimated range. But that is not true. It's actually had some error in the measurement, and your actual distance will be this. This is your true distance. Okay, so there will be always a mismatch because of the noise in the signal strength data. So the path loss, it is not, so this is one component of the path loss. Okay, that is in this equation, and then there you have other components which are related to randomness. Okay, so there is the short term fading and shadowing and so on. So fading, shadowing because of obstacles and so on. So these kind of phenomenon are going to show up, and that is the reason you are going to have a continuously fluctuating RSS value. And to experience this, you can do a very simple experiment. You can install, let's say, a certain application, right, that is going to track your Wi-Fi signal strength and display that, right? You can always write up this small code. Android allows you to read the signal strength of these access points, and you can simply watch that, right? You will see that it is continuously fluctuating. From minus 54 it will go to minus 60, minus 55, minus 48, and so on, right? Of course it is not going to become minus 100, right? But there will be some small scale fading that is going to happen, and that is going to introduce some randomness in the path loss value. It is not exact. Okay. uh, okay, so that is how these errors could be introduced. And there are actually devices that are being sold. You can get these Bluetooth beacons, right? Because Bluetooth transmitters could also be used here, and you can get a pretty good sense of proximity. Okay, so if you are looking at things like proximity detection, for that also it will be very useful, that whether you are in near to a certain shop, or near or whether you are in a certain floor or not. So for those kind of situations it could be useful. And for distance measurement, as you are seeing that at full power, right? So initially this is your the dot dot is basically your measured distance or accuracy, and that red thing is your actual distance. Okay, so if you are seeing here, so 0 to some time, right? We are keeping it at the location number. This is the location 0, or let's say probably the range is like 0 meters or 0.5 meters actually. This is what it is shown, 0.5 meters. In this case, this location was 5 meters, and in this case the location is 15 meters. Okay, and as you see, the accuracy is going to be very poor at higher distances. Okay, so now uh, I will ask you one question. Okay, so think about it. Why does the accuracy suddenly start going up while your distances or the range from the transmitter to the receiver becomes high? What is the reason for that? Okay, let me come back to the particular plot, right? We have done here, or you already have this in mind. What is the reason that whenever you are ranging distance, absolute distance, right? Let's say you are trying to range 15 meters or 20 meters, that is associated with very high errors. Whereas while your distance is like 1 meter, or within 5 meters, let's say, whatever be the case, right? The accuracy is not that very accuracy is not that poor. Okay, so what has accuracy to do with distance?
Sir, maybe the RSS values almost become flat at very high distance, so the we are not able to predict a reliable value.
Okay, so what exactly is like flat? Can you give some more intuition so that like others could also understand?
Sir, maybe in in our in the data for the model, at very large distances we have very low RSS, so the RSS value is flat over the large distance range.
It does not have to do with whether the RSS value itself is low or not. You are correct, but it is not nothing to do with whether the RSS value itself is low. It is low, but that is not the reason. The reason is whatever you have said is the delta RSS does not change. Correct?
Yes, sir. Yes.
The flat in the sense the rate of change of RSS with distance itself becomes less, right? So if you just simply take a derivative of the path loss with respect to distance, you will be able to understand, right? So what you are saying, because in real world we do not use log distance, we normally we use linear distance. If we walk 5 steps, we said we walk 5 steps. If we walk 10 steps, we have double the amount, right? We do not use exponential distances. So in this case, the RSSI changes exponentially with distance. Okay, so initially it is like this. It is going to go down, go down, go down, go down, and whatever you are claiming or saying as flat is probably this, right? So in this case, let me use a different color. In this particular case, the rate of change of RSSI, right? So delta RSSI or RSS and delta D has a different kind of fluctuation, right? Whereas uh, in this particular case, delta RSS and delta D is going to have a very different behavior. Okay, so in this case, you are going to make very much like very high mistakes, right? Or the mistakes will be very too much, right? Because if you simply have this RSSI value and this RSSI value, this could mean this distance or this distance, right? Then that is not going to happen at closer distances, right? Even if the fading is there, right, you will not have this much value difference in RSSI. Whereas while you go to higher distances, even for this much value difference, you can end up in like really large range gaps. Okay, so the takeaway point, whatever you have said is correct, right? It is basically that RSS uh, changes exponentially because we are using this to the power n with respect to distance. Okay, because see, whatever method I showed you, or even it is actually commercially available in the market, this kind of things, right? It is at best good for proximity detection. You cannot do some good localization with such devices, right? And that is the reason. In very close proximity, you can somewhat do a localization, very coarse grained one, and you need to ensure that your range is not much, right? You have to do this entire thing in a small room, let's say. So in a small room, I can tell whether you are on the this wall or that wall, or you are trying to exit the room. This kind of things I can say. Okay, but not more than that. Just using the RSS data, received signal strength data, and now we will try to appreciate how time of flight was so good of an approach. Okay, and you also currently know that RSS has nothing to do with time of flight. RSS is simply the amplitude of your CIR is less. Okay, the signal strength is less, but that is fine as long as I can detect that the packet has arrived. The times are not going to change. Whether the packet is a weak packet or a strong packet, I don't care. As long as I know the packet has arrived, I can find out the time of flight. Okay, there is no dependence on SNR. But in this case, this is so much SNR dependent. And by the way, I have not even brought up obstacles. This was like sometimes line of sight. Now, if you have a furniture or some kind of metals or walls in between the transmitter and the receiver, you will have a different path loss. And this is not scalable. I mean, how many times you are going to go and train this model? So you have to train this model, right? And many of these companies, they have trained certain models and put it in the hardware, and they know these values of slopes and the intercepts that probably only works in line of sight. And they will tell you there will be a star, and they'll say that okay, this only works in these situations. Okay, I mean, if you talk to the industry, many of them will say that oh, this problem is solved, but you have to read the fine prints. Okay, they will say conditions apply, and you have to look at those conditions apply very carefully. If you buy the system, try to install them thinking that it is going to solve your location tracking problem, you will be fooled. Okay, because of this fundamental reason of calibration. Unless and until you calibrate your own system that you have deployed for every link, okay, whatever is going to happen in this room, in the next room it is going to change. So the calibration itself is not going to hold true. Okay, so keep this in mind. I mean, if you just try to use ranging using the RSSI value, this is also ranging, but using the model of this RSSI value, if you can create this calibration model, and again you can create a sophisticated model. Okay, you can do some kind of fancy regression. I told you just you can just do a linear regression with the data. You can do some kind of fancy regression. Still, you have to do it. You have to calibrate it per area. Okay, it is clearly not scalable. It is like again intensive cost will be there. Okay, so this is RSS from Wi-Fi. Okay, and I have shown you as a Linux command in a Raspberry Pi. Right, you can install let's say Ubuntu or some operating system in a Raspberry Pi, and then you can find out using these commands like IW list that can give you the access points that are available around. It can sniff. Okay, so if you do an IW list scanning, it is going to tell you that what are the different access points that are nearby, and what is their what are the signal strength that you can receive data from, right? What is the signal strength of their uh, that you are receiving those packets from, right? So I'll show you a demo on this, right? So let me see, I can So they can start this demo or not. Me, yeah. So you just want to Raspberry Pi, you just check what is the wireless LAN, right? WLAN 0 is the name of the uh, wireless interface that you need to ensure, right? If you are running it in a Raspberry Pi, you can do the same thing on an Android device also, no issues. Okay, so this demo I have done using a Raspberry Pi. First thing is that you check what is the wireless interface, and then you do IW list. If you get acquainted, you can get acquainted with the different things that you can try out with this IW list command, right? And one of them is scanning, right? Probably that is what we are going to use, but there are lots of different functionalities that you can do using this IW tool or IW list tool. Okay, and we are interested in what? We are interested in finding the device's position. The Raspberry Pi position is unknown, and I'm interested in knowing the location of the Raspberry Pi with respect to these anchors. And these, what are these anchors? These anchors are the access points. Okay, so I do IW list WLAN 0 scanning. Okay, and if you do this, you can even do it in a regular laptop, Linux laptop, that is going to give you each an individual access point that it can see. So there are like 10 access points it was able to see, and details of all those 10 access points will be available. Okay, and we are probably interested in, let's say, 3 access points or 2 access points, right? Those access point locations, okay, so in this case, let's say I'm interested only the cell number 1, which is the access point at my home. Okay, or access point number 2. So you can get this entire chunk of information, all the information, what channel or what frequency it is using, what is the signal level, in this case minus 41 dBm. You can see what is the quality. The quality is more like an RSSI. Okay, so you can have access to that information. Then let me skip a little bit. So if you just do, let's say you just do a grep with this address, right? Let me pause here for a certain time. So if you do sudo IW list WLAN 0 scanning grep of address, then you can get this unique cell IDs that are there, right? What are the MAC addresses of the access points around you, okay, or around the Raspberry Pi? So you can see 5 of them. And now you are additionally interested in not just the address, but also the signal quality, right? So if you do an address or quality in the grep option, you can get all these 10 access points. You have the MAC ID and as well as their signal quality. So this is like an RSSI. I told you it is going to be normalized from, let's say, 0 to a number 100, or in this case it is normalized, let's say, from 1 to 70 probably, and from 1 to 70 this gets a number 52. That is the RSSI, received signal strength indicator. And this is the signal level. What is the received signal strength? That is minus 58 dBm, minus 42 dBm, minus 79 dBm, and so on. And these are far off. Minus 89 dBm is very far, right? That's why it is reducing so much. Minus 89 dBm also is there. Okay, so in that way you can get access to the, you can identify from which access point the signal is coming from, and you can uniquely map that to a received signal strength value. Okay, so you can maintain a set. The set will have the access points that are present, and in that and that access point is always going to be associated with some kind of a signal strength value that could be stored in a dictionary kind of a data structure, right? All the time it will be updated. Whenever there is a new signal strength value that is recorded, the corresponding entry for that particular access point will be updated. What is the latest signal strength that you are receiving? Okay, and you can maintain some statistics, how much standard deviation and so on is there. Okay, if there is too much of standard deviation, you would not like to use that particular access point because it will have a lot of range error. Okay, so whenever I ran this command, the next time you can see some of these values have changed, right? And one easy way is to continuously observe such data. So one thing that I have done is I have written a script, okay, and that script is going to extract those signal strength values and the MAC IDs, right? So this is a simple script you can write in any programming language of your choice. It is just that command line option whenever I am giving. that WLAN 0 scanning, IW list WLAN 0 scanning, whatever, the output is going to be fast. Okay, and I'm going to build that level. Okay, so if we run this, so I still just ensure that I am connected and I'm still getting this data. So after that, I'm just going to run the uh, just for the signal level. So whenever I'm running this, I know the MAC IDs and I also know the signal strengths. Okay, so if you see F9, the 8C3B AD, this the one I highlighted earlier. It was 61, now it has become 65. So in just two consecutive runs, there is a difference of 4 dB. Okay, and if you use this watch command, right, watch command is also used if you want to uh, watch this for some amount of time. So if you keep on refreshing this particular output every 1 second, you can quickly see that how much it is changing over time. You can track a particular number, you can actually track a particular access point and keep on looking at the signal strength value. Okay, see, it changes so much. Okay, and the other point is the farther the distance, the standard deviation is also going to increase. You already know that, right? We just had this discussion. Okay, in this way you can simply record it. I just showed you an example using Raspberry Pi. I would like to uh, ask you, you can do the same thing using an Android phone. It's much more easier. There are already applications that can log the signal strength values, and all you have to do, you have to go at different distances from the access point and take this reading. Okay, so this is the demo, right, where I actually collected the data. So this is the access point on the near the wall, and I'm moving my Raspberry Pi, right, and taken a video of that. And on the right hand side, you can see that how the signal strength value changes with respect to the distance. If I'm increasing the distance, how it is changing its value. Okay, so you can take a log of this distance. It will become more linear because the distance is not much inside my home. From 0 to 10 feet I have done in this particular scenario, right? But you can do it in a big field. You can go outside in a big field. You can set up an access point which is like have outdoor transmission powers and a bigger antenna, right? So there are outdoor access points that are also available, or you can use the same thing that you have at your home, right? How much it can support, you can see, right? And this is like line of sight. There's no obstacles or anything, and you just try to plot this. Go every 1 foot and take a reading and save that particular value. Go another 1 foot, take a reading and save that value. In that way, just go 100, walk 100 feet, right? And in that way you can see that how with every increment of distance, how the mean value of the signal changes, because it will be fluctuating all the time. In the right hand side in the plot, I have shown you it is fluctuating all the time. Okay, you can concentrate on the mean value. Okay, remove the outliers and concentrate on the mean value and try to put a regression curve on that. Okay, so this path loss idea is going to help you a lot in fingerprinting also, because when you pick up a fingerprint or a signature, you can have an estimate whether it is near to the access point or not. Okay, so that is how the fingerprinting technique is used. So earlier we were just using the raw value of the RSS and trying to compute or reverse engineer the distance. The other way is not try to do that, but go to different location and collect the RSS value, because of the noise involved, right? Because of like whatever examples I've shown you was in a line of sight scenario. What if there is a non-line of sight? In that case, those path loss models are not going to hold. What you are going to do, you are going to go to these individual locations, go to location 2, collect the RSS data, go to location 3, collect the RSS data, go to location 5, collect the RSS data. It is becoming, I told you in the very beginning, it is becoming very much laborious job. It's heavily dependent on the infrastructure and you require a lot of calibration. Okay, so this location 1 now becomes your level, right? This location 1, this or location I, This basically becomes your label, and this RSS at location 1 becomes your signature. This is a signature or a fingerprint of that particular location or zone. Feature also you can say. Okay, it's a signature or a fingerprint or a feature of that particular location, which is your label in this problem. If you want to model it as a classification problem. Okay, why it is a classification problem? Because given the feature vector, you want to classify what level this data is coming from, and that level is basically your location. Okay, that is what the ML model is going to do. Okay, and as you already have seen, the data changes with location. You will have a unique distribution for every location. Okay, so somebody has to go to these 6 locations. Let's say this is one room, right? Inside a room like this, you are trying to have this indoor locationing built, right? Let's say this is your some room, bedroom or something. Okay, and let's say you divide this room into 6 zones. You have a door here, you have some windows and so on. Okay, you have furniture and all. So you divide this room into 6 zones: 1 2 3 4 5 6, and you collect data for substantial amount of time by going to those 6 locations, and you analyze the data. So what you will see, for every such location you will have a different and unique distribution of RSS. Okay, this is your a histogram I have shown, and you can fit some kind of a probability distribution density function to that particular set of data points. You can always do that, right? Whatever I've shown you is a frequency histogram, right? A frequency spread across the different values of RSSI and or RSS rather, sorry. You can also look at what is the spread. It is like minus 15 to minus 20, whereas this one goes from minus 92 to minus 84. Okay, so whereas this one is so much spread out, minus 82 to 62, but this will be mostly outliers that you can ignore. Okay, so these are the things you need to keep in mind. If there are outliers, you don't want to actually include that in your distribution. Anyway, the frequency will be less, but still you have to be concentrating on sort of a minus 3 sigma to plus 3 sigma sort of a spread, right? And that the rest will be outliers. And some of them, very peculiarly, you will see a very flat distribution. Okay, this is very flat, and flat distribution is a bad news, because you do not have enough information content in it. It is very random. Okay, it could be minus 95, it could be minus 89 also. Okay, so let's say your RSS value is something like minus 92. Okay, this is your RSS value. How do you know which location this data is coming from? This can minus 92, this can come from this distribution of location 5 with some probability. Minus 92 can also come from here with this probability. Minus 92 can also come from here with a lower probability. It cannot come from here. Minus 92 probably cannot come from here. Minus 92 can come from here with a lower probability. Okay, so probably minus 92 has come from either location 5 or location 6. Okay, and with a higher probability probably from location 5. So in that way, you can do the classification job by using something like a maximum likelihood estimate. Okay, MLE is a standard technique that we use, right? So what is the most likely classification level that we are going to assign to that feature vector? Okay, so that is the crux. If you have training data and if you have level training data, you can create a model. We can start with a simple knife based model, right? A knife based model is going to give you that, given this feature vector, what is the probability of a certain location to be true, right? What is the posterior probability of location 1 given the feature vector? What is the posterior probability of location 2 given the feature vector? What is the posterior probability of location I given the feature vector? And what you are going to do, you are trying to maximize the likelihood for whatever location I, it is going to maximize the probability value. That is your maximum likelihood estimate. Okay, you can take a log. If you have lots of them, you can try to, because the numbers will become very small, so it will become a maximum log likelihood estimate. Okay, the likelihood value could be very small, so sometimes we use a log likelihood. Okay, so naive bayes is a like very simple thing that you can start with to appreciate such data, because you can do that experiment that I told you using that Android phone and the transmitter. You walk 100 steps, and at every step you collect this data, right? And you can come back and try to analyze this data. Okay, can you classify? You can solve it as a regression problem, that is a separate thing, but can you do a classification? You have 100 levels, you have like 100 levels starting from location 1 to location 100, and for every such level you have a distribution. Suppose I pick up a random number from that particular data set, can I tell from which distance it was collected from? And you solve it as a classification problem, not as a regression problem. You can get a very good idea how to handle such techniques. Okay, and of course you can read up more online, right? Once you try to look for Wi-Fi fingerprinting for localization, thousands of papers will turn up, right? And you can try to look at the highly cited ones. So variability of RSS, you already know, it could be for interference, it could be for obstacles, and many household objects we might have at our homes that could pose as obstacles, and dynamic obstacles also. So sometimes we come in between the link, right? Human beings can come in between the link, right? So that is going to affect the channel. The channel is affected. Simple thing, you take the phone in your hand and face the access point, you turn around and face your back in the access point direction, because now at that time your body will come in between the phone and the access point, and this will directly cut down the signal. This is an experiment that we have done, and it is plotted, this RSSI, and this is an accelerometer data, just noting that whenever I turn, right, this is basically your turning instant, just to have a correlation in between whenever I have turned, so that the data is registered properly. Whenever I turn my face on the other direction, the RSSI immediately dropped. Okay, so it is so sensitive, right? From -60 it went to like -90 or something. So if you have your body in between, and that is dynamic, right? If it was an obstacle like a furniture, it is always going to be there. So your fingerprinting algorithm might be okay, but the fingerprinting algorithm might not handle dynamics very well. Okay, so dynamics in the sense how spread out is your distribution that you have collected for a given location. It can have a very high variance, and the variance could be because of this dynamic obstacles like human beings. Okay, so you have to keep this in mind also. So for a given anchor or beacon, this function has to be learned, and that is basically going to be a component of your model. Okay, so for every location you collect the data, fit a density function for that model for that particular location, and a collection of them you have to do, not just for one location, for many locations you have to do, and save them in a database in form of a model. Okay, so this is exactly the same thing that I have already shown you. And now the problem is that how unique these distributions are, because if this distribution that I am recording in the last slide I have shown, if distributions are not unique, so suppose at location number 74 I am also getting a distribution that looks very much like this. So this is for 1 and this is for 74. Okay, yeah, this is for 1 and this is for 74. Then given let's say some values that you have collected, you have to classify, you could be confused very easily between 1 and 74. Okay, so the uniqueness of the RSSI is also very important. So in that case, what we do not restrict ourselves to only one access point. We increase the size of the feature vector, and we actually collect the RSS value from multiple access points. In this case, there could be n access points. So this is the size of your feature vector. So your location earlier was a function of just RSS from one AP. Now you have, let's say, 10 APs. So that this multidimensional distribution, there is a very low probability that it is going to be replicated somewhere else. Okay, so all the values of the signal strength that you are getting at, let's say, the location number this one, right? Let's say some location, right? cannot be the exactly the same for all the access points for this location. Maybe two access points will show up very similar very similar values, right? Maybe for this access point, let me color this with this with red with the blue, right? Let's say I'm coloring this particular access point is blue color. So for this particular access point, the RSSI here and here might be same. Okay, but let's say for what will happen for the this yellow access point. Let's say the access point is this one, yellow access point. Okay, so this will be more here. The signal strength will be more here and less here, right? Is there any confusion with this? So somehow the access points, the different positions of the access point are going to ensure that you are going to get distributions which do not look like each other. You will at least have an unique distribution spread across the different locations. Okay, only then you will be efficiently able to identify the location information, right? Classify the location information. Okay. So you basically collect such synchronous strength model, and one example was the naive Bayes that you can use. There is one more example that I am going to tell you, and that was basically the first uh, paper that was published in this particular domain was using k nearest neighbors. I'm going to come to that, but before that, this is the final slide regarding your just to get you the crux of the methodology. Okay, so suppose you have n access points, label them as ap1, ap2 till apn. So there are n access points, and these n access points could be wi-fi access points or even n wi-fi n bluetooth beacons, whatever. They come kind of a wireless transmitter, and you have some set of discrete locations, l1, l2, l3 dot to lk, right? So there are k locations. Okay, and for every such k location you are going to receive a feature vector which is of size n. Okay, this is your feature vector that has rss1 comma rss2 comma rss3 comma and so on rssn. So you have this multi-dimensional feature vector of size n here, and this feature vector will be there for all these discrete locations. So there is a different treatment if you want to bring continuous locations, but for many of the real life applications, it is much better to treat this thing discretely, right? The problem becomes much more simple. Okay, and one more thing is that based on the granularity you want, suppose you want to distinguish in between two square blocks of size 2 meter by 2 meter. Okay, so if you remember the room example that I gave you, so in this example it is your choice whether you want to create a 2 meter by 2 meter block or whether you want to create a 1 meter by 1 meter block. So in that case, instead of having six locations, right, you are going to have like 12 locations, or actually it will be more than that, right? So 4 will be coming from 1, so it will have 24. Okay, so you'll have this thing splitted up, right? So it has become 1 by 1. So 4 is going to come from one of them. So from 6 you are going to have 24, right? So your resolution has really now become much more granular, and now these are the locations 1, 2, 3, 4, 5, 6, 7, 8, and so on. Okay, so this is how you discretize the space depending on what kind of SLA requirement is there. Okay, you have understood this fingerprinting concept, and the ML model that you can use is up to you, right? You can use an SVM, you can use a naive Bayes and so on. Basically this is a classification job, and your primarily goal is to collect such data. And it also might be that you have incomplete data. That is also possible. You might not have an exhaustive collection of this data. In that case, what you need to do, any pointers regarding that? Suppose you have collected data but not collected data for all such cells. Okay, you have collected data for some of them. It is not possible to collect it exhaustively everywhere, right? Because this will become an extremely tedious job. Any suggestions what you are going to do in those cases?
Sir, maybe impute the missing values.
Yeah, I am asking about how to impute, but how to impute? I mean, you have to impute.
So like some sort of matrix completion problem.
No, no. This is, I mean, it looks like a matrix, but it has nothing to do with a matrix here, right? So you
Yes.
have some of the values that has been collected, right? You have collected some of this data here and there, but there are some missing values here. Okay, why I'm asking, this is missing, this is missing, this is missing. It is not possible to go everywhere and collect data. How much you will collect? So what you can, as a first cut, what you can do? That is my question. All of you have heard about interpolation, no? Just interpolate those values. What is the value of this? If I know their neighbors, right, I can always come up with an interpolation scheme to figure out the value of this particular guy from their neighbors. I know the neighboring information. Okay, so from the neighborhood I can come up with some kind of an averaging or weighted averaging based on the distance of me or the black cell with respect to the other cells. Okay, if I know their distance, I can find out something like, let's say the RSS of those cells is like RSS I, and I can multiply that with the weight depending on that kind of the what kind of distance you have from that, and then basically try to find out the average of that, right, divided by sigma wi. That can give you some kind of a weighted version of interpolation, right, depending on the distance. So this di, this wi could be a function of di, right? What is the distance of my missing data cell from the cells that has data? Okay, this is a simple way to fill up this particular thing using interpolation. Okay, so that I have the data complete, because for some of those discrete locations, you might have missing data. So some li, you do not have any data, is missing. Okay, so you basically try to interpolate them in the very beginning, before building the model. It could be erroneous. I'm not saying it is not erroneous. Those are the problems, but there are different solutions to them, right? So I cannot cover everything in this particular lecture, but I'm trying to give you as many pointers as possible such that you can take up these particular things and explore that more on your own. Okay, so this is the end result. After you complete the data collection and you complete the interpolation, you will basically have a fingerprinting database that looks like this. You have features and you have discrete locations, and now you have to put all these things inside a database, and that database, then you can actually create a model out of it. It could be a parametric model, right? And you can also have a non-parametric model where you store all the data, right? So parametric model is basically, let's say a Gaussian, right? Let's say you have an assumption that you uh, model the distribution of the RSS at a particular cell as a Gaussian function, right? Normal distribution. And what is the parameters going to be? You just record the mean and the variance of that, right? It basically is a parametric way to model, right? And the other extreme is a non-parametric way where you do not assume any models, you just store the data. Okay, so that basically, which is known as a non-parametric model, where the raw data is stored. So one example is the radar, and this is one of the first papers that was published. That is the reason I am bringing it up. You can, if you want to read up any fingerprinting related work, you have to first look at least this paper. This was from Microsoft Research in India, Victor, and so I mean joint authors in between. But this work was published from Microsoft Research, and you can look up radar localization paper, Microsoft Research. You can see they were using a non-parametric model. They have done the exact same thing. They had a set of access points and they collected data for all such access points for many such locations. And then instead of using a parametric model, they used a non-parametric model. They used this k nearest neighbors. Okay, so you have such data. Okay, and this is the collected data. I would say calibration data, collected calibration data. Okay, and whenever there is an input, right, so there is a query So your device, your IoT device is going to see that, oh, I have these values of RSSI. Can you please tell me what is my location? Okay, so this query is going to go through this database, and then they're going to run a k nearest neighbor search, right? And I'm assuming that all of you know k nearest neighbors. It is just going to compare the distance of the feature vector that is being queried with all the different feature vectors that you have here, and going to come up with k closest ones, right? And out of them, you know the location, because these are all level data. You know what is L1, you know what is L2, and so on. So suppose you find a good similarity with Li, Lm, and Lj. Okay, so what you can do, you can simply find out the average of these locations, right? And that is going to be the estimate of Lx. Okay, as simple as that. Okay, that is what this radar paper does, but it is a very good starting point, because this paper initiated all these follow-up papers, where they were trying to use Wi-Fi access point, because Wi-Fi access points is like ubiquitously available. It is everybody, in everybody's home it is there, right? And it is extremely easy to collect signal strength data. Most of the hardware is going to expose signal strength information, but they are not going to expose impulse response. Okay, so RSS data is somewhat very easy to obtain. Okay, and that is how you can scale such systems and make the deployment much more easy. So all the thing that you have to do is primarily in terms of the software. Okay, so but why do you think this k nearest neighbors is not a very good idea? What is exactly the problem that will show up if you actually want to deploy such a solution in reality? Can you deploy the solution, and what is going to bug you? If you have some understanding of k nearest neighbors or non-parametric models, you'll be able to answer this question.
So maybe it becomes too dependent on the training data, so it won't generalize to new data.
But we are not even trying to generalize or build a model, right? That is why we are using k nearest neighbors. There is no parameter that is involved. So that part exactly we are not doing. That is the reason that has this has a different kind of a problem. So if we use the parametric model, then whatever you are saying would happen.
Okay, sir.
Okay, but that is exactly not going to happen here. It will be something else. Tell me, I mean, as an engineering problem, right? What kind of deployment problems might come up in terms of performance?
Sir, it takes time to compute all the neighbors.
Exactly, this is a linear search, right?
Yes.
So if this is k nearest neighbors, you have to go through all the data. It is like a n operation. Okay, for every query from a multiple devices, think about the amount of time it is going to take. So the number of features that you are going to have, ideally for a very large region, is going to be several thousands of data, right, points, right? And this is multidimensional. It is not just one RSSI. You might have like 30 RSSI values. Think of like a big office space, right, where like an enterprise Wi-Fi setting, where you might have several tens of access points, right? So there are so many numbers that you have to actually, floating point numbers, that you are basically dealing with, right? And trying to do it for multiple nodes. So scalability is going to be a problem, and that is the reason these non-parametric methods are not quite favored. Ideally, you have to create some kind of a model. Okay, and the model is going to have that problem that you have brought up, that it is not going to work for all the time. Okay, so and yeah, that is what you are going to do. And the other thing was, for continuous locations, you can think that that entire space is continuous, right? Instead of having a discretized set of values or locations, you can create this spatial map of RSS, which is also known as the radio map. Okay, and this is based on interpolation. Suppose you have collected data at some locations. Okay, so randomly you have collected data from certain locations that are labeled. Can you use this data to create or estimate the signal strength anywhere? Okay, so this map of the signal strength is known as the radio environment map. and you will have one such map per transmitter, right? You will have one such map for one AP, another map for another AP, and so on, because depending on where the transmitter is kept, the signal map, REM, it's known as REM, or very you can commonly it is also known as signal map. So all you need is the access to very accurate signal map. If you give me a very accurate signal map, localization problem is solved. But the problem is nobody is going to give you the signal map. The estimation of the signal map is a very tedious procedure, and the signal map changes dynamically because of the location of obstacles changes, human beings move around, there are other issues like random fading and so on. So this map is approximately, it is going to be the same, but it is not going to be exactly the same. Okay, and that is the reason you will need more and more such maps such that you can recognize the location. Okay, so that is how you bridge this gap, by having more number of signal maps. Okay, so I just discussed this thing, right? You have collected some data and you have predicted the entire map, and now given any query, right? Suppose I have a query which is coming from this location, I give the RSS values. You can simply say, okay, this is, I think to the best extent it is coming from this particular location. Okay, so keep this in mind, and more the number of maps you have, better is going to be the accuracy, because this is just you're adding more dimensions to your feature vector, right? From a machine learning standpoint, this is going to work much more better. Okay, and now can you have, so all of them were supervised learning techniques because you were considering the level as well as the feature vector. So now you can think of like what is a practical way to deploy such things, right? You will not have any levels. Okay, what is going to happen if you don't have any levels? Only you have the RSS values. So now the problem is that can you line up these RSS values properly and create this, right? Can you add a spatial uh, dimension to this RSS? Because this RSS data collection is very easy. So you can run an app in your phone that continuously reports the RSS values. But what is the hard problem is that this RSS value has to be mapped to some kind of a physical location. That is a hard problem. Okay, so one idea as a like a research pointer would be to make this complete process as much unsupervised as possible. That gets rid of any calibration efforts, right? The calibration efforts you don't have to give. How can you minimize the amount of calibration efforts and have a robust localization system? Because this takes a lot of money in order to calibrate. Okay, because you have to spend human effort, and this human effort you have to repeat. Anything you change in your setting, right, in your furniture or any other construction, that any changes that happens, you have to redo this process. So this is extremely laborious and calibration intensive. So how can I minimize the dependence on level data and at the same time maintain a good localization accuracy? So that is sort of a problem that still exists, right? And there are many suggestions regarding um, how to address this problem. And this problem, by the way, is not just for Wi-Fi. It also holds for outdoor localization for like cellular companies. So the cell companies, based on the signal strength feedback that you are giving out always as a part of your paging process or as a part of the measurement reports that your smartphone or your phone, right, your phone modem gives out to the cellular ISP or the cell phone providers, they want to predict your location, and you are not giving out any GPS data to them. Although you have a GPS, but because of privacy reasons, because of legal reasons, they are not taking your GPS data. They are only taking your RSS data. Let's say it is possible to know the RSS data. From that, they have to figure out your location. And if they want to do a fingerprinting based approach, they actually have to cover an entire city going around and collecting such data. And that is actually done to some extent, which is known as what driving. Believe it or not, they will take a car, they'll take a vehicle, and they will keep on doing measurements in different roads. They will firstly know what is the performance and what is the location and what is the signal strength, and this data could actually be used to train some models like this. Okay, but exhaustive measurement is not possible. So what I am telling, can I improve on this and make it as much unsupervised as possible? Okay, so that is another direction to think on. So we have sort of discussed all these three approaches: infrastructure free MDS, infrastructure needed TOA, TDOA, and AOA, and some idea about how fingerprinting could be used, and then to train some machine learning models, and the models could be predicting the value of the location. Okay, so we will be left with some pointers uh, for tomorrow, that is going to be on the inertial sensors. Okay, so this is a little bit different. This has nothing to do with signal strength or any anchors or so on. This is just you are getting the local values of acceleration, compass values, gyroscope values, and so on. Okay, but to have an overall understanding, it is better to complete this entire loop by also discussing about IMU. So I'll next day, I'll tomorrow I'll discuss about IMU, and tomorrow will be the last class. So before that, since I have covered most of it, I'm going to have some a small evaluation quiz, just to for yourself to test your understanding. So in the class itself, I'm going to give you a Google form, right? And you can fill up the Google form, uh, just putting the answers there. Okay. So you can expect questions from the first class till today, right? Basic questions. I mean, if you have a simple understanding, you'll be able to answer all the questions. Okay, there will be no critical things, and this will be like maybe a 15-20 minutes quiz. Okay, maybe I'll give like 5-10 questions that could be readily answered, right? If you know the ballpark concepts, right, you will be able to answer them. Okay, followed by we will go into, after completion of this thing, I am going to introduce you to all these concepts related to IMU. And IMU is cannot be just it can be used for location tracking. Okay, but at the same time it can also, there's a lot of applications where these are used for tracking gestures. Okay, what kind of movements you are doing, because IMU is a device that is often residing with you, right, in a smartphone or in your smart watch, right? You can use that for knowing that the person is walking, or the person is running, or the person is climbing stairs, and so on. Okay, so those kind of things are also uh, useful, right, in the localization context. Okay, so I will keep it till here today.